So today we're going to discuss fission, fusion, talk a little bit about something you've probably heard of, the half-life. Okay, fission, fusion, the half-life. But I guess I need to get the right board up because that's not. There we go. So, fission, fusion, half-life. Nuclear fission occurs when a heavy nucleus splits into two smaller, more stable nuclei than what that original nucleus was. Most of these reactions happen by artificially bombarding the nuclei with neutrons. So, this might be a little tough to see if you're in the back. We're going to do a gizmo on this later in the week, okay, that shows you this. But what's happening? This little blue dot you see right here, this is uranium-235 right here. So this little blue dot is a neutron that a scientist has shot at that nucleus. When that neutron hits that nucleus, it splits the uranium into two different elements. This one is krypton here at the top. That one is barium right there at the bottom. But the key part to this is when it splits those apart, it also has three more neutrons that are, so to say, the products of splitting those two. Now, what do those three neutrons then do? They collide with other uraniums to cause more splitting of the nuclei. So these unstable uraniums are split into more stable nuclei by those neutrons. So we started out with one neutron, split it into two. Here we have three neutrons given off, which then collide with other ones. Now, we have three more down here, three more down here, three more up here. So can you see it's kind of like, and we're going to call this a chain reaction. We shot one, and then three neutrons came off of that, which collided with three other ones. Now how many neutrons do we have to collide? Three from each one, so what's 3 and 3? 9, all right? So, as shown in that previous slide, each of the three neutrons that are emitted from the first reaction, okay, cause the fusion of another uranium. Okay, so each of those first three neutrons, okay, collide with three more uraniums to make three more neutrons with each collision. The process that is called is a chain reaction. A chain reaction. These chain reactions occur in nuclear reactors. A fission reaction can produce a large amount of energy. 1 gram of uranium-235 generates as much energy as the combustion of 2,700 kilograms of coal. That's a lot of kilograms of coal that generate the same amount of energy as 1 gram of uranium-235. These fission reactions are used to generate electrical energy in nuclear power plants. Uranium-235 and plutonium-239 are the main radioactive isotopes that are used in nuclear reactions and nuclear reactors. Okay? How many people have ever been at Lake Erie? Okay, if you go up to Lake Erie and you look along the shoreline, you can see a few of these nuclear reactors. They've got the little round bases, maybe steam are coming out of them. I don't think I have a picture of what a nuclear power plant looks like, but I've got a picture of a nuclear reactor right here. Okay? Now, what you're looking at, okay, these three bottom rods right here, those are uranium fuel rods. So those are uranium. These two rods are control rods. Now, what happens is we have this purple coming through here, okay? It is a liquid water, excuse me, it says moderator and coolant, liquid water under high pressure. That's what the purple stuff is. As you can see, this nuclear reaction releases a lot of energy. So that water is going to be heated up. Okay? This is going to be very, very hot. It comes over and it flows. You can see by the arrows that it's flowing in a circle kind of like this. What happens is it comes over here and gets into this little chamber, and this stuff is just water, this blue, light blue stuff right here. That is just water. What happens is this very hot coil here causes that water to boil. When water boils, it makes steam, right? Steam rises, comes up through here, and here is a steam turbine. Okay, this is a steam turbine. So this actually takes the steam and spins the turbine to generate electricity, an electric current. Well, what happens back with the steam? The steam then comes down here because it's cooling off. Okay, the steam comes down here. Here is cold water. Okay, this is what we call a condenser. That steam touches that cold water and condenses back into water. And then it cycles back up through here. So this water, okay, starts off water here, comes through here, gets heated up into steam. All right? This steam then travels in here, spins the turbine, creates the electricity, comes back down into here where it's condensed back into water. Okay? So that is a kind of generalized version of what's happening inside a nuclear reactor. That was fission. Let's talk now a little bit about fusion. Nuclear fusion is when we have smaller nuclei combining to form larger, more stable nuclei. So in fission, we had a large nuclei that was broken down to two smaller, more stable nuclei. In fusion, we have two smaller, less stable nuclei that come together to form a larger, more stable nucleus. Fusion releases greater amounts of energy than fission does for the same amount of mass. If you have the same amount of each material, you're going to get more energy through fusion than you would through fission. Now, the biggest example of fission, the biggest example of fusion, and we see this daily, is our sun. Okay, our sun is undergoing fusion to generate the great amount of energy that it releases. Now, what are some uses of this nuclear chemistry we've been talking about? Well, the first one is the half-life. The half-life. And all that the half-life is it's simply the time required for half of a sample of a radioactive substance to disintegrate by radioactive decay or natural processes. Okay? The time required for half of the sample of a radioactive substance to decay. Here's a chart that has different half-lives. If you can look, uranium-238 has a half-life of 4.5 times 10 to the 9th years. So half of the uranium-235 decays in that many years. It changes, though. Not everything's the same. If you look, right here's carbon-14. We use carbon-14 in trying to find the dates. It's called carbon-14 dating. So carbon-14 has a half-life of 5,570 years. So half of the carbon-14 decays every 5,570 years. Okay? Look right here, radon-220. Its half-life is in 52 seconds. So some of them are taking literally hundreds and hundreds and thousands of years. Some of them are taking seconds. Okay? Lithium-8, right here. And I don't know why they have two lithium-8s. You would think that they would have the same half-life. I just now noticed that. I'll bet you one of them's a different isotope of lithium. Okay? But look at this lithium-8. 0.84 seconds is its half-life. Now, if you look at this slide, this is how we calculate half-life. All right, I'll go ahead and let you copy this down, and then I'll talk about it here. So as I'm looking at this, this is showing me, it says, the half-life of carbon-14 is 5,570 years. We saw that on the previous table. How many years until 1/8 of a 50.4 gram sample of carbon-14 remains? Now, if you look at this, you'll see something like this on WebAssign, okay? And you'll see this 50.4 gram. Does that have anything to do with your half-life calculation and answering this question? No, it does not, okay? It does not. Now, if we're looking and we start out with 100%, it takes 5,570 years for half of that to decay. So now I've got 50%, right? Takes another 5,570 for half of 50%. So what's half of 50? 25. What's half of 25? 12.5, right? So to get 1/8, which is 12.5%, it takes 3 half-lives. If I add those 3 up together, it'll give me 16,710 years. Now, like I said, the half-life, this is just the half-life of carbon-14. Okay, you saw there are many different things. If we would have taken lithium-8, right, which was 0.84, we're going to have a 0.84, a 0.84, and a 0.84 seconds. So it's going to get to that 1/8 fairly quickly, right? Whereas this carbon, it's taken 16,000, almost 17,000 years. Okay? So, they use that carbon-14 for radioactive dating. Okay, they use those radioactive isotopes to determine the age of an object. Okay, most of the time they're using carbon-14. Now, what are some other uses of nuclear chemistry? Okay, some other uses of nuclear chemistry. Smoke detectors. Okay? Smoke detectors. Remember that Americanium 241? Okay? That's the radioisotopes that's used in smoke detectors. Dealt with that with our worksheet yesterday. Okay? Detecting art forgeries. If somebody sits there and says, hey, I've got a painting from Picasso that I just found in my attic, and they go back and they do radioactive dating on it and determine that it's 50 years old, do you think that Picasso painted that? Okay, so that's another way. Not just with art, okay? They can find all kinds of other things that they use this radioactive dating to try to determine if it were actually possible. Okay, nuclear medicine. Nuclear medicine is a third one. Okay, talked about what? Iodine 131 is used to treat thyroid cancer. Okay, fluorine 18 on your worksheet last night. Fluorine 18 is used in PET scans to study your brain functions. Okay, so we have many uses for this nuclear chemistry. Okay,